In this lesson, we're going to talk about combinations. Combinations are the number of ways to choose k elements from a set of n elements. The number of ways to choose k elements or k objects from a set of n objects is n factorial divided by k factorial times n minus k factorial. And the notation is written with this parentheses and n over k, although there's no bar in the middle. So some people get a little confused with fractions the first time they see this. It's not a fraction. So here's the notation blown up a little bit, and notice that there is no bar here. It's just n over k with parentheses, large parentheses around it. And that means n factorial divided by k factorial times n minus k factorial. We're going to show two proofs that this is the number of ways to choose k objects from n objects, and the reason I'm doing two proofs is because one may resonate with you more than the other. The first proof uses permutations. So let's let a1 through an be a random permutation of the n objects. And we're going to choose the first k that come up in that permutation. So for example, we might choose a1 through ak. Well, we know that there's n factorial permutations of n elements. But as long as the first k elements are the same, we always end up with the same k. So there's no order in this. We're just picking k. You can think of choosing, k flavors of chocolate or something. It doesn't matter that the first one is orange and the second one is lime. It's just like there's an orange and a lime. So order doesn't matter. And so no matter how those first k elements show up, it's always the same k elements. And that means we're going to get k factorial repetitions that we need to divide out. Also, there are n minus k elements that we didn't choose, and there are n minus k factorial ways that those could be arranged. So to cancel the repetition, we need to divide by the n minus k factorial permutations of those elements. And so that gets us this n factorial total ways to rearrange n objects, and then we have to divide out the k factorial permutations of the k objects that we do choose, and then we have to also divide out the n minus k factorial permutations of the n minus k objects we did not choose. So I like that proof because it's real short and sweet, but it's a little non-intuitive. So we're also going to do a proof using the multiplication rule for counting. That brings us to proof version 2. So each choice we make is going to be an experiment whenever we're choosing the k elements. So we choose the first element, and we have n choices to choose the first element because there's n elements total. For the second element, there are only n minus 1 choices remaining. And for the third element, there are n minus 2 choices remaining. And you can continue doing this until you get to the kth element, and there's going to be n minus k plus 1 choices remaining. And notice that the pattern is always n minus k plus 1. So for the first element, it's n minus 1 plus 1, or n itself. For the second element, it's like n minus 2 plus 1, which equals n minus 1. For the third, let me maybe write this, so it's n minus 2 plus 1, which is just the same thing as n minus 1. This is n minus 3 plus 1, which is just the same thing as n minus 2. And the first one is n minus 1 plus 1, which is n. So when we get down to the kth choice, there's n minus k plus 1 choices remaining. And by the multiplication rule, that means there are n times n minus 1 times n minus 2 down to n minus k plus 1 choices, if we choose the k elements in a particular order. So the previous proof was an unordered proof. We can also do, this proof is actually an ordered proof. But we don't want to count order. We just care about the k elements, right, that we choose. So we have to, once again, cancel out the k factorial permutations of the elements. So we've chosen them here in order, but then we have to cancel out the repetition once again. And that gets us this formula. We just need to show that this formula equals n choose k. So that's the goal. And that's just a little bit of algebra. So we have this product of n to n minus k plus 1 over k factorial. And what we're going to do is multiply by n minus k factorial on the top and bottom. So here's n minus k factorial on the top and n minus k factorial on the bottom. And then on the top, what we're multiplying is n times n minus 1 all the way down to n minus k plus 1. But then n minus k factorial would also include n minus k times n minus k minus 1, and so on down to 3 times 2 times 1. So this actually just ends up being the product n all the way down to 1. And that is n factorial. And that's how we get this, which by definition is n choose k. So let's do an example. Suppose a company wants to choose 3 colors to create a logo, and the designer suggests 10 colors to choose from. How many different color combinations could they choose to make their logo? Well, they're choosing 3 colors from a set of 10 colors. So the number of choices they have is 10 choose 3. And 10 choose 3 is by definition 10 factorial divided by 3 factorial times 7 factorial. So 10, this 3 is from here, and then the 7 is 10 minus 3 factorial is equal to 7 factorial. So that's where that comes from. And this 7 factorial is going to cancel off 1 to 7 in the 10 factorial. So you're left with 8, 9, 10 on the top, and then the 3 factorial on the bottom is just 1, 2, 3. And multiplying that out, you get 120. So there are 120 possible color combinations if you're going to choose 3 colors from a set of 10 colors.